Hello everyone, this is Dr. Young, and in this video I'm going to introduce to you the technique called calorimetry, where we measure the calories of something, or in other words, we measure the heat of a certain process or transformation. So let's talk about this. It's a method, like I was saying, it's a method of determining energy changes associated with the physical and chemical transformations. So physical being like temperatures going up and down, or phase changes like melting or boiling, something like that. And then chemical transformations like a reaction, like combusting something or hydrogenating something, or any kind of chemical reaction, really. And the idea is that this can be used to determine the specific heat or the heat of a reaction, right? Heat of reaction, the delta H reaction. And so I'm going to show you in this video how to do both of these calculations. And what we do with calorimetry, because we're trying to figure out the amount of heat that's been transferred from some unknown process, is that we use a very well understood substance, usually like water, to determine that change in energy. And you want to keep in mind for us, right, since we're not doing PV work, our change in energy is equivalent to our change in enthalpy, which is equivalent to our Q, our transfer in heat, right? So all of these terms are kind of interchangeable here. And so what we do is we do a reaction or a process in water, and then we see how much water changed. And if we know how much water changed, we know how much heat was going on with water, how much heat was being transferred in or out of water, we can then infer that that other thing was the thing that was either gaining or taking away the heat from water. And I'll show you more what that means in a sec. And then we do calorimetry in a calorimeter. So we do it usually in some sort of container called a calorimeter. And ideally, this is an isolated system so that no energy can go in and out and no mass can go in and out. So it should be nice and sealed is the idea. And calorimetry is really based on this first law of thermodynamics, right? We said that energy is neither created nor destroyed, so it has to be conserved. It's just changing forms, really, right? And so what that means then is that the energy of the system, the thing that you're studying, plus the energy of the things around it has to be equal to zero, right? If you lose 5 kilocalories here, you must gain 5 kilocalories here, so it all equilibrates out to zero. And we, like I said before, our change in energy, we are defining as just Q. It's just that heat transfer is the same thing as delta E. So I just replaced my delta E with system to get my Q's. And these two equations right here are like the same thing. These are the same thing. The only difference is that I went ahead and I subtracted the Q of the surroundings to get it onto the other side. So you have that the Q of the system is equal but opposite to the Q of the surroundings. So the amount of energy that is gained or lost by the system is equal and opposite to the amount of energy gained or lost by the surroundings. And so that's the basis of all of the calorimetry calculations that we're going to do here. Is that one, we're gonna see what the Q is for the thing we know, and then infer what the Q is for the thing that we don't. And we're gonna use the formulas that we've already seen in previous videos. So what is calorimetry? Let me kind of show you how this is set up so you mentally have an idea of what this is like. And let's just say that the question here, right, is what is the specific heat of mithril, which is a fictional metal, right, from Lord of the Rings. I'm a huge nerd, but let's just say let's just say we don't know, right, what the specific heat is, and how would I find it out? Because obviously, I can't just look it up on Google or in some reference book, right? I got to figure it out myself. So the first step is that you heat a known amount of mithril up, right? So when you heat a known amount, right? So in this case, I know that it's 23.8 grams, right? You just weigh it out. And then you heat it to a known temperature. So usually what you do is you just boil something, right? So this is supposed to be a hot plate. This is supposed to be a cup of water, a beaker of water, and you just boil it. You just boil the bejesus out of it for a while. So that's why I wrote 100 degrees here, so that you know that the metal is the same temperature as the boiling water. So you've got it at a known temperature, right? So you put all this energy into the metal. You've raised the metal up to 100 degrees Celsius. And then you take that hot metal, or that 23.8 grams of hot mithril that's at 100 degrees, and you dump it into a known amount of water at a known temperature. So in this case, I'm saying, well, let's put 120 grams of water in here, and let's just say it's at room temperature, which is about, well, 24 is a little high for room temperature. It's a hot day. But let's just say it's at 24.0 degrees Celsius, right? So I have a known amount of water at a known temperature. I dump in these hot mithril pieces. And so, of course, the water is going to start getting hotter, right? You take room temperature water, you pour hot metal into it, and then the temperature goes up. So what you're doing is you're waiting for the system to equilibrate. You're waiting for this temperature to go up and then basically stop so that they've transferred heat between one another and your system's equilibrated so you can see how much heat was transferred from the metal to the water. And if you want to draw these, right, I can draw the Q's just to kind of see it, right? We would say that the heat, the energy goes from the metal to the water, right? Or in other words, the Q for the metal is going to be a negative number. It's losing heat. And the Q for the water is going to be a positive number because it's gaining that heat, right? It's heating up. And so that's kind of the basic process, right? You heat up a piece of metal to a known temperature, you throw it in a bunch of water that you know information about, and you see how much the water goes up. And by that, you're able to figure out what the heat capacity is of that metal. And so let me show you how. So remember that I said that our Q1 plus our Q2 has to equal 0, right? The total heat transfer in your process, it has to equal out. Or in other words, what I'm saying is that the heat from my mithril plus the heat of the water is going to equal 0, right? Because they're equal and opposite. Because whatever the mithril lost, the water gained, right? In this process right here, the mithril lost heat to the water because it went from hot to cold. And then the water gained that heat. And the idea, again, is that it's equal and opposite. So what I'm going to do here is I'm just going to go ahead and subtract the Q of the water from both sides. This is just a lot of algebra. So that I get the Q of my mithril equals the negative Q of my water, right? They're equal and opposite. But what are these Q's, right? Well, I already have equations for the Q's, right? We did all these Q equals like M delta H VAP for when you're trying to boil something. Or we did Q equals MC delta T when we're trying to heat something up. And that's what we're doing here, right? We're heating and cooling things. So my Q's, I'm just going to use that. Let me draw this right here. I'm going to have one for my mithril, where I'm going to have my MC delta T for my mithril, and I'm going to have a MC delta T for my water. And so those are what I'm going to use for my values of Q. So I'm going to use for my values of Q. So let me rewrite that over here, actually, just to kind of emphasize this, right? So MC delta T is going to equal the negative MC delta T, right, where this is for water, and this is for the mithril. And then I just start plugging in my numbers, and I'm going to solve for the specific heat. So, for example, with the mithril, I know that the mass of the mithril, the M, is 23.8 grams. I don't know the specific heat because that's what the question's asking. I don't know what the specific heat of mithril is. But I do know the delta T, right? The final temperature was 28.1. That's what it says over there on the far right, 28.1 degrees Celsius. And the initial temperature of my mithril was 100 degrees Celsius. So that's how I'd figure out the heat transfer for the mithril. Now we also have the water. What was the mass of the water? This M for the blue stuff. The mass of the water was 120 grams. The C for water, you would go and look that back up, but that's 4.184, right? Remember, joule, gram, degrees Celsius. And what's the temperature change for that water? Well, the water ended up at 28.1 also, but it started off at 24.0 degrees Celsius. And so I can just start solving now for this, right? So I'm going to start solving. I'm going to get, if I do this, I'm going to get negative 1,711 times the specific heat. And over here on the right, I'm going to get negative 2058 joules. Right, and I guess I should say that this, I'm being sloppy with my units. I apologize. So negative 1711, this will be in gram degrees Celsius, would be the units, if I'm keeping my units together. And so I need to isolate C, so I'm just going to divide by 1711 grams times degrees Celsius. grams degrees Celsius. And so I get that my specific heat for mithril, if I divide those out, is 1.20 joules per gram degree Celsius. That's my specific heat for mithril. And notice that if you keep track of your units, they'll all make sense, right? All of our specific heats were in something like energy per amount degree Kelvin, something like that. So hopefully you see what I kind of did here, right? I took stuff I knew about, which was water, and I used it to figure out something I didn't know about, which was the mithril, right? Specifically, the specific heat of mithril. So let's look at a question that's going to look more like from a textbook or a test or something like that. Here it's saying a 6.02 gram of iron at 100 degrees is placed in 25.0 milliliters of water at 22.6 degrees in a calorimeter. The temperature equilibrates to 24.5 degrees Celsius. What is the specific heat of iron? So we're going to set it up the same way. I'm going to have the Q for the iron plus the Q for the water from the calorimeter. I know that equals 0. And I'm just going to go ahead and subtract my Q on either side so that I have an equation to work with here, right? Q of my iron equals the negative Q of my water. Again, both of these things are changing temperatures. So I know that I'm just going to have my MC delta T for my iron is going to equal the negative MC delta T, but for the water. And then I just start plugging in my values. I know my iron is 6.02 grams. I'm solving for the specific heat of iron. I don't know what the specific heat is, but I do know the change in temperature, right? I know that I end up at 24.5, and the iron started off at 100 degrees. And then I will put in, so that's all the information for the iron, so equals negative Q, so now all the water stuff. Sorry, I switched my colors. I wasn't trying to be color specific, but whatever. So for the water, how much water did we have? Well, so here's a little extra piece we have to do. I need grams of water, but I'm not given grams of water. I'm given milliliters of water. You may have heard this before if you have not. Water at normal temperatures and everything is just 1 gram. There's just 1 gram of water per milliliter. So really, you can just say this is 25.0 grams of water. Now, at different temperatures, this kind of varies, but not at room temperature. So I'm going to say that there's 25.0 grams of water. The specific heat, again, is 4.184 joules per gram degree Celsius. And the change in temperature, again, it ended at 24.5 degrees Celsius, but water started at 22.6 degrees Celsius. And so I'm going to solve all of that so that I get negative 454 gram degrees Celsius times C equals negative 198 joules. Again, I'm trying to solve for the specific heat, so I'm going to divide both sides by 454 gram degrees Celsius, whatever that unit is. So those suckers cancel. And then that's going to leave me as my specific heat equals 0.436 joules per gram degrees Celsius. And that would be the specific heat of iron. Right, it's telling me that a gram of iron that to heat up a gram of iron, it requires 0.436 joules to raise it 1 degree Celsius. So that's the specific heat of iron, right? But it's the exact same problem as the previous slide. It's just a little more wordy, less pictorial. But the key thing, again, is it's all about the first law of thermodynamics, that we cannot create or destroy energy. So whatever the energy is that the iron is giving out, it's being absorbed by the water. Since we know so much about the water, we can then infer back things about the iron. So let's look at a slightly different question, even though it's the same concept. This one's asking how much will the temperature of a cup of water, 180 grams, at 95 degrees be reduced when a 45.1 gram silver spoon, and then they give us the specific heat for the silver, at 25 degrees, it's placed in the water and the two are allowed to reach the same temperature. All right, so I got two things going on here. I've got what's going on with my silver spoon. Here's how much silver spoon I have. Here's the temperature it is. Its specific heat. And I have a sample of water. I have 180 grams of water, and it starts off at that temperature, so hot. So the idea is I have a hot cup of water. It looks like I have a hot cup of water. It's at 95 degrees, so it's near boiling. And then you're putting into it a spoon that weighs, what, looks like 45. Weighs 45.1 grams, but it is at room temperature. It's at like 25 degrees Celsius. So we're trying to see what the end temperature is going to be. But really this question is like all the other questions, right? The heat transfer from the spoon plus the heat transfer to or from the water has to equal 0. Or in other words, the heat transfer of the spoon is going to be equal but opposite of the heat transfer of the water, right? So the Q spoon equals the negative Q water. And then same thing, we're just going to start filling up all of the information that we know, right? So for the spoon, I know a lot about the spoon. I know the spoon's mass, right? Again, we're going to use the MC delta T. So I know the spoon's mass. Right, I know the spoon weighs, what did they tell us, 45.1? 45.1 grams. I know the specific heat, they told me it's 0.24 joules per gram degrees Celsius. And I know the change in temperature is T final minus T initial, but I don't know the TF, right? That's the whole point of this question is, I want to know what the final temperature is when they're allowed to reach the temperature, right? How much will it be reduced? What's the final temperature? I don't know that, but I do know that the spoon started at 25, right? The spoon started at 25.0 degrees Celsius. I do know that. And I know that that energy is equal and opposite to what's going on with the water. The water was 180.0 grams. The specific heat is 4.184 joules. Kind of run out of room here, sorry. Grams degrees Celsius. I don't know the final temperature, but I do know that the water started off at 95. Barely made it, 95 degrees Celsius. So what I'm going to do is I'm just going to multiply a bunch of this stuff up here. I'm going to draw it in black now just to keep it all the same. But I just wanted to emphasize, right, that I'm doing the same equation, but for the two different components, right, the system and the surroundings. For me, I'm kind of thinking about the spoon as the system and the water as the surroundings, because the spoon is the thing that, I don't know, it just seems like seems like it's surrounded by something. It doesn't matter which you call which. It's going to be the same math either way you do it. So if I multiply this stuff together, right, so if I take my 180 and I multiply it by my 4.184, I'm going to get that is 753.1 joules per degree Celsius times this TF minus 95.0 degrees Celsius. If I do the same thing on the right-hand side, sorry, this is a negative. Do the same thing on the right-hand side, and I'm going to get 10.82 joules per degree Celsius times my TF, 25.0 degrees Celsius. Now, if you're paying attention to the units, right, I said joules per Celsius here, and that's just because the grams cancel here, and you're left with joules over Celsius, which is why I got joules over Celsius. Now, the point here is that I'm trying to isolate TF. I'm trying to solve for TF. So how am I going to start isolating this? Well, there's a couple ways you can do this. I'm going to use the TF on the right-hand side just because I got to pick one. So I'm going to divide both sides by negative 753.1 joules per degree Celsius. And this is all just algebra that I'm doing. I know that it looks kind of like I'm doing craziness, but I'm just doing algebra. So now those units cancel right there. That is going to give me negative 0.01437 times that TF minus 25. Which is going to equal now my TF minus 95.0 degrees Celsius. I'm going to expand this out here, right? I'm just going to multiply this out so that I've got negative 0.01437 TFs minus, what that turns into a plus since you're multiplying a negative there, plus 0.3593. And again, that'll be in degrees Celsius. And so, right, all I did was I multiplied this first number, the 0.01437 times TF. That's how I got that. And I multiplied 0.01437 times 25. So I got that, right? And the two negatives cancel each other out, which is why that's a plus. Again, just algebra. So I'm here. I want to get things together. So I'm going to go ahead and I'm going to add 95 degrees Celsius to each of these. So now I've got negative 0.01437 TFs plus 95.4 degrees Celsius. I'm trying to watch my sig figs here. Equals this TF. But I got that TF on the other side, so now I have to add. I'm trying to get this all together. I'm almost there. Sorry, 1437 TFs. Then that finally gives me 95.4 degrees Celsius equals 1.01437 TFs. Oh my gosh, I'm running out of room, but we're going to make it barely. 37 TFs. And then I'm almost there. I just got to divide both sides by 1.0. Am I going to have enough room? I got to really smudge this. 1.01437 TFs. And I'm dividing each side by that 1.01437 so that I get the TF all by itself. And I'm going to divide the left side also. What was this? This was 95.4. And then what you get, and I've run out of room, but what you're going to get is that your TF, you get 94.01 degrees Celsius equals TF. Or in other words, that is your final temperature. That your final temperature of that situation should be 94.01 degrees Celsius. Or in other words, adding that silver spoon to your water reduces it about 1 degree Celsius. That's what all of that work just said. But again, it's the same idea as before. You start off with these two Qs. It's just the algebraic manipulations are a little more annoying. And you could do this so many different ways. I don't care which way you do your algebra. It's just as long as you get to the right, as long as you're able to isolate your TF and get to the right answer, you're going to be set. So let's look at one more type of problem. Those were both for having two objects and you're transferring heat between two objects, but you can also calculate the heat of a reaction. So I wrote here H delta H reaction. The RXN stands for reaction. But there's lots of delta H's. There's a delta H of COMB, which stands for combustion. There's delta H's for, just so many things. There's delta H's for hydrogenation, for any kind of reaction, really. For dissolving things, for just all kinds of things. So how do you figure out what the heat changes for something that's a process, right? A reaction's a process. It's not a hunk of metal. It's not a silver spoon. It's a occurrence. It's a thing. So it makes it kind of weird to think of a reaction as being like something that's going to absorb or release energy. But in fact, that's what it is, and that's what you have to do. So in this question, it's saying that you've got 10.9 grams of propane and that they're allowed to combust in a calorimeter containing 100 grams of water. The temperature of the water rises from 22.6 to 35.1. What is the heat of combustion for propane? Right, so it's a similar idea. Again, I'll draw out a little thing so we can kind of see this. But the idea is that you'd have your calorimeter nice and sealed. You have a thermometer in it. Terrible thermometer. You have water. And then you have a container in here in which you're going to combust your 10.9 grams of propane. Right, so this is just going to ideally go boom. And then you're going to see heat gets transferred out of this to the water. But again, since we know so much about water, we know its specific heat, we know the amount of water, we know the temperature of water. However much the temperature of the water changes is going to be indicative of how much energy came from or went into the reaction. So it's going to be the same thing. The Q of our reaction is plus the Q going on with our water, the heat transfer of our water, is going to equal 0. Or once again, right, the idea is that the Q of the reaction is going to equal, but be opposite of the Q going on for the water. Now, what's nice for us is, since the Q of the reaction is not a thing, I'm not going to use like an MC delta T because it doesn't have a mass. It doesn't have a specific heat or anything like that. But I do know all of this stuff about water. So I know my Q of my reaction is going to equal the negative of all of this stuff about the water, right? The MC delta T of the water. So the mass of the water was given to me. That's 100 grams of water. The C, I know that's 4.184 joules. Again, that's something that you if you haven't figured out already, is a common number you're going to use over and over again. You should definitely have that at your fingertips. And then the temperature change, the final was 35.1. It said it went to that, and it started off as 22.6 degrees Celsius. And then so we can just solve for that, right? So now our Q of the reaction is going to equal negative 5,230 joules, right? And so this is the Q, this is the energy released, right? It's negative, so it's released. So I'm thinking about my next words. The energy released by 10.9 grams of propane burning. So that's good to know. However, the question is, what is the heat of combustion, but in kilojoules per mole, right? So they want to know, well, what's the heat of combustion, the delta H of combustion, which is the same as, right, our reaction, Q of our reaction. These are the same thing. Remember we said that this could have been delta H of the combustion plus the delta H of the water equals 0. It would have been the exact same thing, right? We're just using Q instead. But I need this, right? I need my delta H of this combustion, this delta H of the reaction, to be in kilojoules per mole. Now, kilojoules, that's going to be easy enough. I can just convert this. I can just take this number here and turn it into kilojoules. So that'll just be negative 5.230 kilojoules. Easy breezy. But I need to figure out the number of moles, right? Because I didn't have a mole of this. I only had 10.9 grams. But that's easy enough to do too, right? I know that 10.9 grams of C3H8, I know how to convert that into moles. All I need to do is figure out the molar mass of C3H8. And if you add up those 3 carbons and those 8 hydrogens, you'll see that it weighs 44.01 grams per mole. And so that's going to tell you that in that 10 grams, it's 248. So that's what I'd put down here. 0.48 moles. And then I'd just take the 5.230, divide it by the 0.02348, and then I'd get, as my heat of combustion, negative 21.1 kilojoules per mole. And that would be my heat of combustion for this reaction. And I just made up these numbers. I don't know if this is the right one, but that's how you would use calorimetry to figure out the heat of a reaction, whether it's combustion, hydrogenation, precipitation, an acid-base reaction, any sort of reaction whatsoever. You just do it surrounded by water, see how much the water changes temperature, and then use that as your proxy that's equal to and opposite the heat change of your reaction. So definitely practice these. Then my next video, I'm going to talk more about heats of reactions and heats of formations. So keep an eye out for that. Keep studying. Good luck.